Introduction to polarization. So, polarized light is basically not a natural phenomenon. Polarized light is not produced naturally. It is obtained using some optical elements. Process in which we transform unpolarized light into polarized light is termed as polarization. So basically, polarization is a phenomena of transforming unpolarized light into a polarized light. Polarized wave is the light wave with definite direction of E vector in a single plane. This is very much important to remember that polarized wave is the light wave which will have definite direction of E wave or E vector, right? Polarized light will contain waves that only fluctuate in one specific plane. Light is polarized when its electric fields oscillate in a single plane rather than in any direction perpendicular to the direction of propagation. So these are two phenomena of polarization. As you can see, it will have only single direction, either it is vertical or it is horizontal, right? So that is a polarization. Now, polarized light will not be transmitted through a polarized film whose axis is perpendicular to polarization direction. If the polarization direction is vertical and the film is perpendicular to it, it will not propagate, right? So here you can see this can go only if it is a vertical, not in this particular way. When light passes through a polarizer, only component which is parallel to the polarization axis will be transmitted. If incoming light is plane polarized, the outgoing intensity is given by I equals to I0 cos square theta. So here you can see light direction is here. Incident beam is polarized at an angle theta, as you can see here theta, right? So this is light, this is incident light which is polarized at angle theta to the vertical and has amplitude of E theta. When it passes through a vertical polarizer, only vertical light which is E0 cos theta, that is this particular y-axis value, will pass through it. So whatsoever incoming is there, only outcome will be the one which is parallel to the axis of polarizer, right? So remember this is very important phenomena with respect to polarization. So this basically means, or to understand this phenomena more clearly or more specifically, we can see this particular figure. This means that if initially unpolarized light, you can see here unpolarized light, the light is having this vertical direction and this random direction at some angle theta, right? So when this light passes through a polarizer which is having a vertical axis, so this is a vertical axis polarizer. When this light will pass through this, only vertical light will be able to pass or surpass this film. So this vertical lines will pass through this and the angle theta will remain as it is. Now, when this vertical or plane polarized light, which is having a vertical axis, passes through a horizontal polarizer or horizontal analyzer, no light will be transmitted to the other side. Why there is no light transmitted to the other side? Just because the direction of this polarized light and analyzer or polarizer is different. If they are parallel to each other, then they will surpass, and if it is not, then it won't be transmitted, right? So this is the phenomena. Light is also particularly polarized after reflecting from a non-metallic surface at a spatial angle called the polarizing angle or Brewster's angle. The polarization is 100% and that is given by tan theta p, that is theta of polarization is equals to n2 by n1, right? So this is with regard to polarization. Now, when unpolarized light reflects off a non-metallic surface, the reflected ray is partially polarized and plane of polarization is parallel to the reflecting surface. This can more be understood by Brewster's angle. So this is a figure, if you can see here. This is a slide and there is an unpolarized light which is incident on the plane. This is normal, that is 90 degree to the plane, and this is polarized light which is reflected from this particular plane. The theta angle which is made by unpolarized light when it is incident on the surface is given by theta p. And this is a polarized light which is coming out, right? So this theta p is slightly polarized refracted ray. Now, according to Brewster's angle, at a particular incident angle, the reflected ray is 100% polarized along the plane parallel to the surface. This occurs when angle between reflected and refracted ray is 90 degree. When the angle between reflected and refracted, that is, this is a reflected ray and this inside one is a refracted ray. So if you can go back and see, right, so this is a reflected ray and this one is a refracted ray, right, slightly polarized refracted ray. So when the angle between reflected and refracted ray is 90 degree, 100% polarized will occur, right, or 100% polarization will occur. Applying Snell's law, we can say n1 sine theta p is equals to n2 sine 90 degree minus theta p. Theta p is incident angle of unpolarized ray on the surface, right? So that is given by n2 cos theta p, or we can use tan theta p equals to n2 by n1, which is our so-called Brewster's angle, right? Now, let us see polarization by double refraction. So what do we understand by the word polarization by double refraction? Light passing through a calcite crystal is split into two different rays. This process first reported by Erasmus in 1669, right? And that's why it is called double reflection or double refraction. The two rays of light are each plane polarized by the calcite such that planes of polarization are mutually perpendicular. For normal incidence, the two planes of polarization are also perpendicular to the plane of incidence. For normal incidence, Snell's law predicts that angle of reflection will be 0 degree. In case of double refraction of a normally incident ray of light, at least one of the ray must violate Snell's law, right? So for calcite, one of the two rays does not indeed obey Snell's law. This ray is called ordinary ray or O ray. Remember that ordinary ray is termed as O ray. So this is the case of double refraction. And according to Huygens theory of double reflection, a point in a doubly refracting of birefringent crystal produces two type of wavefront. The wavefront which is corresponding to O ray is spherical wavefront, and ordinary wave travel with same velocity in all direction, and so the corresponding wavefront is spherical. The wavefront which is corresponding to E ray is ellipsoidal wavefront, and it is extraordinary wave, have different velocities in different direction. So the corresponding wavefront is elliptic. Now, production of polarized light. So, plane polarized light and circularly or elliptically polarized light. There are these two main categories. So, when we talk about plane polarized light, when monochromatic unpolarized light is allowed to fall on nickel prism, the beam after passing through it is plane polarized, right? And when nickel prism is kept at some distance from N1 and N2, is rotated such that no light will come out of it, a quarter wave plane is mounted on a tube. The tube will then rotate about the outer fixed tube introduced between N1 and N2. Now the quarter wave plate is rotated such that no light come out of N2. Keeping P fixed, A is rotated such that mark S on P coincide with mark. So this is actually an circular or elliptical light. Now let us see how they are produced. So plane polarized light. The light beam is allowed to fall on nickel prism if on rotation of nickel prism intensity of emitted light can be completely extinguished at two places in each rotation, then light is plane polarized. When we discuss about circularly polarized light, the light beam is allowed to fall on a nickel prism, as you can see here in the picture, right? It will allow to fall on the nickel prism if on rotation of nickel prism the intensity of emitted light remains same. Then light is either circularly polarized or unpolarized. To differentiate between unpolarized and circularly polarized, what we need to understand is the light is first passed through quarter wave plate and then through nickel prism, right? So these are the two cases. If you can see here, circularly polarized light, quarter wave plate is here, so it will pass through a quarter wave plate. Plane polarized light will be there, then there is a nickel prism which is analyzer, and you can see here variation in intensity with minimum intensity 0, right? So this is it. And when unpolarized light is passed through a quarter wave plate, unpolarized light will be generated here, and when it is passed through a nickel prism, no variation in intensity will be found. Talking about detection of plane, circularly and elliptical polarized light. So now let's talk about elliptically polarized light. So what do we mean by elliptically polarized light? The light beam is allowed to fall on nickel prism, as we have already seen in last two cases. If on rotation of nickel prism the intensity of emitted light varies from maxima to minima, then light is either elliptically polarized or a mixture of plane polarized and unpolarized. Then how we can differentiate? We can see here in these two figures. Elliptically polarized light, when passed through a quarter wave plate, it will generate a plane polarized light. And once this plane polarized light is passed through a nickel prism, which is our analyzer here, it will generate variation in intensity with minimum intensity 0, right? In other case, when partially plane polarized light is passed through quarter wave plate, partially plane polarized light is generated on other side of quarter wave plate, then it is sent or passed through nickel prism or analyzer, and at the end of it we can see here variation in intensity with minimum intensity 0. So this is the difference between both the cases. Let's discuss about optical activity. So the ability of a substance, whether it is crystal or solution, that's why we are mentioning here substance. The ability of a substance to rotate plane of polarization about the direction of light is called optical activity. The substance, whether it is crystal or solution, which can rotate plane polarized light is called optical active substance, right? You can see here, this is the substance. When it is passed through the prism, you can see here no light, and here you can find some kind of light. So there are two type of optically active substance, dextrorotary and levorotary. So what do we mean by dextrorotary? The substance which rotate the plane of vibration in the clockwise direction, right, with respect to observer looking toward the source from the analyzer, then it is known as dextrorotary. Example is quartz crystal or fruit sugar. When we talk about levorotary, the substance which rotate plane of vibration in anti-clockwise, just opposite to dextrorotary, right, in anti-clockwise with respect to observer looking toward the source from the analyzer, then it is a levorotary. An example of this is cane sugar solution.